Everyone, it's Mr. Reedy back with yet another video. So today, guys, we're going to talk about 6.2 energy diagrams and 6.3, which is the heat transfer and thermal equilibrium. So guys, let's first talk about how to read our energy diagram, right? So you'll notice that the x-axis is labeled as the process of the reaction. Sometimes it's called the reaction coordinate. So that's the x-axis. On the y-axis is what we are measuring our potential energy, okay? And that is often in kilojoules, okay? Now, the two parts of the graph that we need to talk about now is this hill, right? The hill from where the reactants start to the top of it, and then, of course, the energy from the reactants to the products, okay? So this hill is called our activation energy, or EACT, and it's simply the energy required for a reaction to occur. This is the energy that is breaking the chemical bonds or the intermolecular forces so that the atoms or molecules are able to interact with other atoms or new molecules during a chemical reaction. So that is our energy of activation. And guys, it occurs at the top of our hill down to the energy of where the products are. That is the activation energy, or EACT. Okay. Now, delta H is the energy, okay, that is absorbed or released from or to the surroundings. And it's simply the difference, guys, from the reactants and the products, the difference in energy between the reactants and products. So here's my energy of my reactants. It's in purple. Here's my energy in products. It's also in purple. The energy difference between them, okay, which is in purple right now, is my delta H. Okay, so in this case, energy is being released, and the energy that's being released is my delta H. Meanwhile, the energy that I need for this reaction to occur is the activation energy, or EACT. Okay, let's continue on. For endothermic reaction, guys, heat is being absorbed by the system from the surroundings, okay? And in this case, the reactant, you'll notice, guys, is at less energy than the products because energy is being absorbed in this process. So products will have more energy than the reactants in an endothermic reaction. Let's continue. In an exothermic reaction, heat is being released or emitted from the system to the surroundings. So in this case, guys, my energy of my reactants is going to be more than the energy of my products because this amount of energy is being released. Okay, so reactants to products, if the products are less energy, we're looking at an exothermic reaction. All right, the enthalpy of reaction is simply the amount of heat generated or absorbed by a chemical reaction. Guys, generated, we could also think of it in terms of emitted, okay, or released. Okay, those are synonyms of generated, just to keep that, just so we're aware of that. Those are two synonyms of each other, okay? So our delta H of our reaction is equal to the sum of the delta H of our formation of our products minus the sum of the delta H of formation of reactants. Guys, we're going to pick up with this equation later on in the unit, but I figured I introduce it now. Moving forward, when we're talking about delta H, guys, I'm probably going to give you this value, and it won't be into a later subsection before we start to actually calculate it. So I just wanted to introduce it for now. So this is going to depend on the amount of reactants that actually react. That's pretty simple to state, right? It will be positive for endothermic reactions, negative for exothermic reactions, and delta H will be labeled as the difference between the energies of the products and reactants. Okay, so that's essentially what this equation is stating, but for right now, it's more important for you to understand what's happening, which is why I labeled it in blue. Okay, let's continue on. Okay, so the activation energy, guys. So you'll notice, guys, in A, the evacuation energy is low, which means this reaction is going to happen fairly quickly. Okay. So since the activation energy is low, this chemical reaction will happen very quickly. Conversely, if the EACT is very high, this reaction will occur slowly. Okay. So just keep that in mind, guys, is that your evacuation energy, which is simply the energy from the top of the hill to the energy of the reactants. If it's small, fast reaction. If it's high, slow reaction. Okay. Keep that in mind as we move forward. Okay. How do we draw energy diagrams? The first step is to label your axes. Then you're going to draw the reactant and product lines. Step 3 will to add the hump or the hill, so we can indicate our activation energy and find our delta H. And then finally is to label the different parts of, so we label the activation energy and then the enthalpy change, delta H, as we continue. So copy these steps down, guys, and then we will do an example problem on the next slide. So here is our example problem. Consider the following reaction. So it says chlorine trifluoride reacts with ammonia to form nitrogen gas, hydrofluoric acid, and chlorine gas. It gave us that our delta H is negative 1,196 kilojoules per mole. It wants us to draw the reaction pathway for this reaction, and we have to label the reactants, the products, and delta H itself. So let's start off, guys, by first drawing our axes. So I'm going to put on the x-axis reaction progress. It'd also be acceptable if you chose to say reaction coordinates, but I'm going to put reaction progress. Okay. Now, our y-axis, of course, is going to be our delta H, right? Or, in other words, our potential energy change. Okay. And our potential energy change will be, in this case, kilojoules, because that's the unit they gave us in the problem. So we'll put kilojoules in parentheses. Okay. And now my next step is to draw the reactant and product. So real quick, guys, this negative sign right here means that we're looking at an exothermic reaction. Okay. So since we have an exothermic reaction, right, we have to make sure that the products have less energy than the reactants at the end of this chemical reaction. So I'm going to put my reactants here and I'll put my products down here. Okay, I'll label them R for reactants and P for products. Now, if this was the AP exam, guys, I would definitely be saying that R is equal to CF3 plus NH3. Okay, and then that P is equal to N2 plus HF plus Cl2, just because I want them to know what R and P stands for, right? No reason for them to take off silly points. And then, guys, I'm going to draw the hump or the hill, and then I'm going to connect my two values. So it's going to look something like that. Okay, it asks us to label delta H. So let's label delta H. Delta H, again, guys, is going to be the energy, the difference in energy between the reactants and the products. So I draw my dotted lines like this. Okay, and this difference is delta H. Okay, and delta H in our case is negative 1,196 kilojoules per mole. Okay, that's delta H. Now, it didn't ask us to find the energy of activation, but we'll do it anyway. So the energy of activation is simply from the top of my hill to my reactants. So it would be this value here. This would be our EACT, or energy of activation. That being said, guys, that's as simple as these problems are. So again, just follow those 4 steps from the previous slide and you'll be good to go. One thing I will state is if they give you more specifics about the equation, so this problem was very general, but if they were to give you specifics about the equation, make sure you're taking the specifics into account, especially if they're giving you a graph that has the axes to scale. So just keep that in mind if you see a question like that in practice problems or on the AP exam itself. All right, so catalysts, what do? They will lower the activation energy of a chemical reaction. In a biological system, a catalyst is called an enzyme, and then catalyst, guys, will not affect delta H. So, guys, if you take a note here, look at how much energy of activation was lowered by this introduction of a catalyst, okay? So, by introducing this catalyst, guys, I was able to lower the activation energy pretty substantially. However, my delta H did not change, right? My delta H remained the same value because, again, a catalyst is simply lowering the energy of activation. Now, where have you guys probably seen a catalyst before? Probably in that elephant toothpaste demo that we've seen. So, guys, remember, essentially all elephant toothpaste is the productions of suds between hydrogen peroxide and whatever soap you have. Now, what makes elephant toothpaste cool is the introduction of a catalyst, right? Which is mostly in the form of potassium iodide. I've also seen it used with yeast, okay, like a yeast slurry that you use in baking. And what simply happens with the yeast slurry or the potassium iodide, it activates the reaction much faster, which is why you get those really big bravado jumps of the hydrogen peroxide shooting out of the container and producing the suds much quicker. So that's what a catalyst is. Guys, you'll notice that I didn't talk about the definition that is italicized. We will review or revisit that definition when we talk about kinetics in Unit 5. All right, so the Maxwell-Boltzman distribution curves. Guys, I just want to review these now that we have a new lens to look at them in the form of now we're in Unit 6. So we have a bit more under our belt in terms of chemistry. So let's revisit this. Remember, temperature is simply the measurement of the amount of kinetic energy of particles in a sample. And guys, if I'm graphing the kinetic energy of the same gas, but I'm comparing it via temperature, you'll notice that the higher temperature one has more kinetic energy, right? Because it's at higher temperature. Remember, kinetic energy and temperature are directly proportional to each other. Meanwhile, the gas at lower temperature has lower kinetic energy. Pretty simple there. Okay. Particle diagrams, right? So at any given temperature, particles will have a range of kinetic energies and a range of speeds. Kinetic energy equals 1/2 mv squared. Some of the particles will be low speed, but most will be close to the average speed, and a few will have high speed. Guys, that's simply what these arrows are showing, is that the particles have different speeds, but the average of them is your kinetic energy, okay? They all share the same average speed, okay? Now, guys, we can also look at the Boltzmann distribution curves and compare gases of different mass. So now these gases are all being held at the same temperature. That means they all have the same kinetic energy, but however, their speeds are different because speed is directly related to its mass. So the lighter mass you have, the more speed the particle is. So you'll notice helium has the highest speed and argon or xenon has the slowest speed. However, in terms of their kinetic energies, they all have the same because it's at the same temperature. Okay? All right, heat transfer and thermal equilibrium. So thermal equilibrium or heat transfer is when two substances of different temperature are combined, the thermal energy will flow from the hotter one to the cooler one. So we use this idea that the Q of our system is equal to the negative Q of our surroundings, and heat can be calculated from the following equation. So Q equals times the specific heat capacity CL, so delta T, where Q is heat, M is your mass, CS is the specific heat capacity, and delta T is the temperature. Okay, so in this case, guys, our system was hotter than the surroundings, so the heat flowed out into the surroundings. So that's why the temperature increased in the surroundings, because that's where the thermometer was. Meanwhile, in this one, the system was cooler than the surroundings, so the heat flowed into the system, which is why we measure that the heat decreased. So again, heat is going to travel from the hotter substance to the cooler one. So if the system is hotter than the surroundings, the heat flows from the system to the surroundings exothermic. Okay, that's what A is. Now, if the system is cooler than the surroundings, the heat is going to go from the surroundings and into the system. So that's what's happening in B. Okay, so guys, I am going to make a separate video for this example problem. So make sure you watch the example problem in its own video. With that being said, guys, that's the end of today's video. I'll see you on the next one.